Okay, let's try this again. Dear students, this is my 5th attempt at recording this lecture. So this is the second part of this morning's lecture, during which I was accidentally muted and I could not hear your cries for help. I'm sorry about that. We'll try to do it again. So in previous attempts, my tablet was always crashing and I only noticed a few minutes later, so I'll be looking at the camera a lot this time. All right, so again, I'll go a bit faster because some things are already written on the iPad from my previous attempts today. You have the lecture notes to follow along as well. And if you're not an ETH student and you're just watching this on YouTube, we try to put most of the lecture materials here on this website, SQuID.ch. Wait, and I have a new problem. The pencil doesn't work now. Okay, there we go. Good. All right, so this morning we did evolution of arbitrary states under uniform dynamics. And today we'll just see very briefly about independent systems evolution. And then we'll talk about evolution of observables and a little bit about conserved quantities and symmetries. Yeah. Good. So what is the idea? So is that we have several systems. We could have more here, C, and so on. And there's a joint Hamiltonian, right, acting on everything. However, for many physical systems, as you saw in the end of the first part of the lecture, we can find like a sensible decomposition of the global Hamiltonian into local terms. So this one acts only on A and does nothing on B. This one acts only on B and does nothing on A. And then whatever is left, we call the interaction Hamiltonian. For some physical systems, this will be obvious. For some of them, maybe HA or HB will be 0, and then you have only this part, which makes things a bit more complicated. So today we look at the simplest possible case, which is when this term here is 0. So we only have these local terms, and we call this, in this case, we say that A and B are non-interacting systems. And what we'll show now is that in this case, we can, if you look at the evolution of the two systems together, we can decompose it into the independent evolution of system A and system B. Good. So what we'll do, and don't worry if this looks too full, I will zoom in. There we go. There we are. So we have our unitary, which is just the exponential of the Hamiltonian with the time and some constants. Good. We expand this Hamiltonian here, and it's this big thing. So this is all a very big matrix that is a bit cumbersome to work with. So ideally, we'd like to split it into two matrices. And since we have here a sum of two parts that seem more or less independent, we'd like to decompose this into the product of two exponentials. So let's see that we can do this. On the right-hand side, I have here the building blocks needed. And these are some that you saw in the tutorial. First, does everyone remember what the commutator of two matrices is? So this is just, excuse me for a moment, it's just this thing here. So the commutator of M and N, I represent it like this. It's kind of common notation, although it depends on the field. And it's the first matrix times the second minus the other way around, okay? And this gives you a notion, well, we'll see later what this is, but it gives us a notion of whether they can you can evolve one system than the other. So not also if you can observe two things at the same time or not. We'll see many applications of this later on. Don't worry about it. Good. So what you saw in the tutorial, this is tutorial 3, so you can go back and watch that if you haven't yet, is that if two matrices commute, then the exponential of the sum is the product of the exponentials, just like if they were real complex numbers, right? Oh, sorry, just complex numbers, not matrices. If they don't commute, then there's a bunch more terms here that can get very complicated very quickly. but we don't look at this case. But now we still need to see that our matrices commute. And this is the other thing you did in the matrix, in the tutorial, which is that if you have a matrix that acts only on one system, you did it for unitaries, but this is true of normal matrices in general. And one that acts only on the other system, then they commute. If you don't remember why this is the case, you can do it by hand now. But essentially, is that the inner product was such that when you multiply them, all the system A is on one side, all the system B is on the other, and identities commute with any matrix, essentially. So they give you this for free. So if you don't believe this, this is a good time to stop and try to do it by hand. Good, so now we apply that here. We say, well, this matrix commutes with this, so we can write the exponential of the sum as the product of the exponentials. Perfect. What's the problem? We still have these identities here on top, which seem like a bit cumbersome to carry around in the exponent. And ideally, we'd want to do something like this, which is to just bring them down. And so let's see that we can do this. So the trick is always, so let's start with the exponential of some arbitrary matrix on the first subsystem and identity on the second. We do, as per usual, like you did in the tutorial, we do a Taylor expansion of the exponential, okay, which is the sum over n, 1 over n factorial, and then whatever was in the exponent to the power of n. So we solve this exponent first. And, this is just MA tensor the identity times MA tensor the identity, and so on, many times, n times, which means that you have like all the MAs on one side, tensor all the identities on the other side, okay? So that's what we have here. But now, of course, that identity to the power of n is just the identity. And if it's just the identity, it no longer depends on n, so we can put the brackets here, so we can just take this identity outside of the sum. Okay. And now what are we left here? Well, this is again the Taylor expansion of an exponential, but now of a matrix that's acting only on system A. So this is just exponential of matrix A. And this identity on B carries out, is still here. So what did we show? That if you have the exponential of a matrix on A tensor the identity on B, we can take this identity out of the exponential. So we do it here. Whoop. We were up here, and we just take this two exponentials down. Good. So what we do now? Right. So now we have this big matrix multiplied by this big matrix. So we just multiply them in the usual way with the tensor product, meaning that on the left on subsystem A, we have this times this. There we are. And on the right, subsystem B, we have this times that. There we are. Okay. Now, of course, the identities are not doing anything here by definition. So we're just left on the left with this, which is the exponential of a Hamiltonian times the time t times the usual constants. And here again, another Hamiltonian times t and the usual constants, which means that this is the unitary that describes the evolution of subsystem A as if it was evolving only under Hamiltonian HA for time t. And here, same thing, is the unitary that describes the evolution of system B according to this Hamiltonian HB for time t. And that's it. So we started, this is how the whole sheet looks like. We started trying to compute this global unitary that describes the global evolution, and we found out that it's just a tensor product of the individual unitaries. So to go back to our picture, is kind of exactly this thing here. So we can decompose it like this. What happens if this h int is not 0? It gets much more complicated, but if it's small enough, we can kind of bound it into semi-local terms. And this is what is used, for example, in Hamiltonian simulation. If you want to simulate the Hamiltonian of a large system through local interactions, then there are some tricks one can use in quantum computing to do this. So maybe we'll see this later in the semester, maybe not, depending on the time. Good, so that's what we'll do for now for evolution of independent systems. We will see some evolutions where this is very much important. This is the case, for example, of measurements, where A could be the system I want to measure, and B is kind of a pointer system on my measurement device. And we will see this later in a week or two. Good. So now we change topics to talk about evolution of observables. And what's the idea here is that maybe, I prepare a particle, an electron, in a very fine-tuned state, and I evolve it over a very complicated Hamiltonian. But at the end of the day, I just want to know one property of the electron, like was it likely to hit a screen? Or how far does it go? So when am I expected, when should I expect this electron to hit the screen? Meaning that I don't care maybe about the whole wave function, but I just care about some properties of this. And if I can write this property as an observable, then what I mean is that I don't care about how the whole state evolves, but just some properties of this observable. And as you'll see, sometimes there are tricks that we can use to try to find answers to how does some property evolve, like how does the average position of the electron evolve in time, that are simpler than computing the evolution of the state and then the average of this property at the end. So that's the main idea. So let's just recap what our observables took. As we saw, these are a way to represent measurements where we already integrate our labels for the measurement. So it's the sum over all possible outcomes L of the projector that represents this outcome times the label. So for example, this could be our 10 centimeters or +1, -1. So this is in general, for everything to work from now on, we take this to be a real number, which makes the matrix Hermitian. Good. And now just for some notation, so remember that the average of an observable, we deduced that it was represented by this, it was computed by this inner product of the state, the observable and the state again. We represented it like this. And if it's at some time t, well, then it's exactly the same. So we just replace the state with the state at time t. And just so we don't have to write this whole thing all the time, we can represent it in this simpler way by just putting a and t. Okay. So only do this when the initial state is clear from context. Okay. Again, if the state is clear from context, you can even leave it out here, but in general, it's a good idea to keep track of things. Okay, so now we will study only a very specific case. And this is where it crashed the last time. So this is as far as I've made it. So consider only uniform dynamics, meaning again that the Hamiltonian doesn't change in time, and time-independent observables, which means what? This is important. This means that this matrix H of H, so these projectors here, these eigenvalues, don't change over time. It has nothing to do with the evolution of the quantum state that we're measuring. It has everything to do with the evolution of the measuring apparatus, okay, your measuring devices on the lab. So in most cases, on many experiments that we do in a lab, on Earth, like stable, it will be the case that it's time independent. Okay. When does it change? Well, if we keep, I don't know, rotating the screen in which the electron must hit, or if I'm trying to measure the direction of a magnet in relation to the magnetic spin, the direction of a magnet in relation to the North Pole. But if I'm really careful, then I know that magnetic field of the Earth changes slightly over the years, right? If I was doing some long-term measurements, I'd have to correct for this. Or if I'm measuring the magnetic field, but I keep changing or rotating something in the lab. Okay. So in most cases, we will not change the observable in time. And the question is, how does then A of t, or how does the average evolve in time? So we just do it. So to see how it evolves in time, we want to know what happens to the time derivative. So let's do it in a new sheet. So we want to know how this evolves in time. So A of t evolves in time, which means we want to know the time derivative. So let's just see. We just plug in the definition. Okay. And now, it's like the derivative of a product is the first times the derivative of the second plus the second times derivative of the first, right? And remember that A does not depend on time. If you did, you'd have this extra term, and I think you did it in one of the tutorials. So let's do the other one first. Chuk plus okay. So now we need to do something about these derivatives, and we'll just plug in Schrodinger's equation. So I'll just write it here. Remember, Schrodinger's equation. And we just write it with all the constants on one side. Okay. So this is one ingredient that we need. And the other ingredient that we need is that if we have ddt of anything in the transpose conjugate, that's just how do I write this? Let's write it like this. You do the derivative of the usual thing, and then you take the transpose conjugate of that. So remember, this is really just changing columns and signs. Good. So what do we get here? A. I'll just replace this thing here. So this was minus I over h bar h plus, and now I over h bar, and here it would be h dagger, but h is Hermitian, so h dagger is the same as h, so I can just keep h. Okay. This is a property of the Hamiltonian. Now, what we see here is that, look, we have this on the left and this on the left, and this is just a vector again. And then we have this on the right and this on the right. It's just a vector again. So we're just gonna plug them out and make a sandwich. Okay, here's the other one. And let's see what's in the middle. So we have minus I over h bar h a h plus I over h bar plus I over H bar H A. Okay. I over H bar is just a constant, so we can take it out of this. And then what we're left with is what? Well, we're just left with HA minus AH, right, because of this minus sign. And that's just a commutator between H and A. Okay, that's HA minus AH. Okay, so this whole thing is what? Is I over H bar. And now, look, if H and A are both Hermitian, right? The Hamiltonian is Hermitian, A is Hermitian, then AH is also Hermitian, HA is also Hermitian, and this sum or subtraction is also Hermitian. So this, you can think of this as a new observable. And this is sandwiched by a state, which means it is just the average value. Okay, so this is just the average value of this new observable at time t. Okay. What does this tell us? Well, it tells us that if we want to know how some observable evolves in time, first we need to compute the commutator with the Hamiltonian. This is going to be the most important thing. And then we still need to evolve the state and then compute this in a product at a time. But what the trick here is that sometimes this thing is going to have a very easy form. So in some cases, it's going to be just a constant, for example. And then, if it's just a constant, it can come out, and you know that this in the product is always 1 because the state is normalized. So it becomes very simple. And we'll see some examples in a bit, but let me just give you some more special cases. Oh, no, you didn't. No, it didn't crash again. Okay. It did not crash. I uncrashed you. Good. Special case number 1. HA equals 0. Then if this is 0, then this whole thing. Then this is 0, then this whole thing is 0. So then this average is 0. Of A of t versus 0. Which means that A of t is constant. In particular, if these two commute, then this means they share an eigenbasis, which means that all eigenvectors of A are going to commute with H, which means that not only this average will be 0, but also other properties of the observable will also not change in time. So in this case, we say that A is a conserved quantity. This is just the physicist term for it. Yep. And, it makes sense, right? It means it doesn't change. It's not changed by the evolution, so it's conserved. Like pineapple. Good. An obvious example is when the observable that we're looking at is the energy, because the energy is just represented by the Hamiltonian. And the Hamiltonian, of course, commutes with itself because all matrices commute with themselves, which means that energy is always a conserved quantity. Okay. Good. Let me just do one more example. We didn't do this one in the lecture, but so suppose that this is a constant. Is some constant, let's call it beta. in C. Okay, so then what is d dt of A of t? Then that's I over h bar. And then here we have the state. We have our constant. We have the state. But that's at A beta h bar times the state in a product with itself, which is just 1, right? So this is just 1. And you're going to see that this is a lot, happens a lot for continuous systems. When you look at position and momentum observables, we'll see it happening a lot. Okay, so in this case, the nice thing is that even though this commutator is not 0, it's a number, we still don't need to compute the exact state at a time t, because we know that this inner product is always 1, right? So we know that we can compute how the average of this property evolves in time, because we just say, well, it evolves linearly, and so on, right? There's other examples like this. Good. A related concept is that of symmetries. So it's very similar to conserved quantity, but now it's for unitaries. So symmetries. And this is applied to a unitary matrix, V is the symmetry with respect to some evolution. If we take our initial state, we evolve it, and this is the same as evolving it as, sorry, I'll explain it in a second, let me write. Okay. So they're saying that taking our initial state, evolving it in time, and then applying this unitary is the same as taking the initial state, applying the unitary, and then evolving the results. Okay? Let me give you an example. Okay, an example is, see, this pen is moving horizontally, okay, and my V is a unitary, so it's a physical transformation. Could be moving it vertically. Yeah? So it's moving there. So I can either let it evolve and then shift it vertically. It ends up here. Or I can shift it vertically first and then let it evolve. Okay, ends up in the same place. So this vertical shift is a symmetry with respect to this evolution. That's this horizontal evolution. An example that wouldn't be a symmetry would be, so suppose that the evolution is now going in the direction of the pen, so from the bottom to the tip, and my V shift, instead of moving it up or down, is just to flip it a little bit, so turn it a bit, rotate it a bit. Okay, so then if I do it at the end, it goes, and then it rotates a bit. So I end up with a pen down here, just pointing up. Or I can rotate at the beginning, and then it goes up, and we end up here after time t. Right? So it's two different final states where it can be. So this shift, this rotation V, is not a symmetry with respect to the evolution of walking in the direction of the pen. Got it? Okay, so those are two examples of what's a symmetry or what is not. And let's just put this in simpler mathematical terms to see what this means. And like, look, if this must hold for all initial states, so if two matrices must commute when applied to a state, this does not mean necessarily that they commute. But if this is true for all initial states, then this is true in particular for taking the states as span a basis. So in the end, this means that they do commute. Yeah? So this means that V and U of t must be 0 for all times. And what is u of t? So this means that e minus I t a to h bar for all times. And again, if this was only true for one time, it did not imply necessarily that v must commute with h, but if it applies for all times, then it means that indeed v and h must commute. Okay? And the relation between symmetries and conserved quantities, which for now doesn't matter much, it's just like 2 more names to memorize, but later on we'll see some examples of this, is that if A, and also this is an emission matrix, is an observable, is a conserved quantity, then this is the same as saying that the exponential is a symmetry for all alpha, all real alpha, and the other way around. So if you only had here one specific alpha here and not the for all, then this direction would not necessarily be true. Okay, one example would be, well, if alpha is 0, then this thing is always a symmetry, because then this thing is just the identity, right? But it doesn't mean that any matrix I put here is a conserved quantity. But if it's true for all alpha, then A must be a conserved quantity. So there's just one more thing I want to do before releasing both you and myself from this time loop, which is seeing an example. So we go back to our example that we did this morning of the qubit evolving in time. And if you don't remember it, I can write it here. So it was a qubit. And the Hamiltonian was just proportional to the Pauli X matrix, where B is some constant. And some real constant, I think. And let's look first at A being the Pauli X observable. Okay, want to know how the Pauli X evolves in time. And this one is very simple because, well, we just do it. So this is going to be I over h bar of hx time, but what's hx? That's bxx, which is b, and the commutator of a matrix with itself, this is always 0, right? So then this whole thing is 0, which tells us that the x direction is a conserved quantity. And this makes sense, again, if you think of this evolution as, so z, x, y. And the Bloch sphere as it rotating around, rotating the Bloch sphere around the x-axis, right? So you might take state 0 to minus, and this state here on the y direction will also change, but the states that lie here on the x-axis don't change. So in particular, state plus and state minus will not change in time. Okay. Good, which means that if you take any state and you're interested in measuring it in this x basis, then you know that this doesn't change. But now let's see another example. So suppose that now we're interested in the z component of the spin, and this is much more complicated. So the x of z of t, I average bar. And let me just write here the, no, I'll do it properly. Z of t I over H bar, and this is B XZ at time t. And now we need to compute this. And you know, we could do it in direct notation, but these are 2 by 2 matrices, so it's easier to just write the matrix and multiply them. So what's X matrix? This. What's the Z matrix? 1 minus 1 minus 1 minus 1. So multiply the 2 matrices, and I just want you to trust me. This is the result. And the other way around, you get 1 minus 1, 0. And this is 0 minus 2, 2, 0. And I'll just rewrite this in a different form, which might not seem very intuitive at first. But this is minus 2i times 0 minus I 0, right? I mean, you can see that this is true. Like, why would you do this? But if you multiply I times minus I, you get 1. With the minus sign, you get minus 1 here. And with the 2, then you get minus 2. And the same thing here. So the maths work out, but why would you do this? We do this because this is actually the Pauli Y matrix. And in fact, it's a very funny relation between all of them. So we'll see this later on. The commutator between X and Y is going to be 2Y times the Z matrix. And the commutator between Y and Z is going to be 2I Y matrix. And the only reason we got the minus sign here is because the order of this is flipped. But if we done ZX, then we get rid of this minus. Okay, so we plug in this result here. Equals I B H bar minus 2I of this observable Y at time t. So this gives us what? 2B over H bar observable Y at time t. And that's that. So it tells us that if we want to know how the state is at time, how the Z component of the spin is doing at some time t, then what we need to do is to look at how we want to see how it changes. Then when it's changing time, ddt. Oh my God, why did I do here? So I hope you got this. This is ddt. Good. If you want to do this, you only need to look at the Y. And similarly, so the relative evolution of Y will depend on this, so it depends on Z. Yep. So it's a bit like, if think of a continuous system, and if you think like, oh, what's the time position, what's the time derivative of, say, the position, that would be given by the velocity, right? So it's like the corresponding of the velocity for observable Z is observable Y. And the funny thing here is that then the velocity of observable Y, because of this property, if you put here Y, you'll end up with Z here and a minus sign there. Okay? So it's like Y is the velocity for Z and Z is the velocity for Y, which is kind of confusing, but later on we'll see many examples. Okay. However, the maths are clear, right? This is how we do the observation of the evolution of observables. Good. I did everything with qubits up to now. And from the next lecture on, we'll start looking at continuous systems where the math is a bit more involved. But then we just need to apply all the results there. Yeah. So see you next time. And thank you for joining me.